The next problem is still about the connected particles. Specifically, this is an example of objects connected by rods. So our reference is still a Cambridge mechanics book. So this is the problem. A model train consists of an engine, locomotive, coupled to a chain of 4 tracks. The coupling between the engine and the first track and each coupling between tracks are modeled as rigid rods. So as what we discussed in the previous example, when we're going to model it as a rigid rods, so we don't consider the mass of the connector. So the train is moving on a straight horizontal track. The engine has mass 0.8 kilograms and each track has mass 0.2 kilograms when empty. The resistance to motion is 0.06 Newton on the engine and 0.01 Newton on each track. The driving force produced by the engine is 3 Newton. So a mass of 0.1 kilogram is placed in each track. So this is the first problem. So find the tension in each coupling. So we are asked to find the tension in each coupling, provided that in each track there will be a mass of 0.1 kilograms. So what we're going to do here, first things first, is that we need to draw a diagram to show the forces acting on the engine and each track. So let's try to draw. So remember that we will be making use here of the laws of Newton. Basically, we will be using the second law, which is F is equal to ma. But before that, we need to start first with the diagram so that we will be having a bird's eye view. You'll have a bird's eye view of the problem. Okay, so let's start with the engine. So our engine will look like this. So suppose this is our engine. So based on the given problem, so the driving force is 3 Newton. So we have the driving force, which is 3 Newton. After that, we're going to have the mass of the engine is 0.8. Okay, that will be 0.8 kilogram. So therefore, the weight will be 8 Newton. Now, going upwards, of course, we have your R. Okay, that will be your R going upwards. And then, what are the resistance? So based on the problem, the resistance of the engine to the motion is 0.6. So that will be 0.6 Newton. What else? So we have here, of course, you have here your tension 1. Okay, you have here the T sub 1, or you can say that this is the tension 1 of the coupling. Now, based on the problem, we're going to have 4 trucks, chain of 4 trucks. So that's the engine. Next, let's start with the first track. Okay, the first track. So in the first track, let's have the first track. So based on the problem, the mass on each track is 0.01. Okay, so this will be, the mass is 0.01. However, there is an additional weight that was given on the problem. Oh, sorry. So according to the problem, the mass of each track is 0.2 kilograms. Plus, on problem letter A, there will be additional mass of 0.1 on each track. So therefore, we can say that this one will have 0.3 kilogram as mass. So if the mass is 0.3 kilograms, so automatically the weight will be equal to 3 Newton. Then this is your T sub 2 or the tension 2. That will be your T sub 2 or the tension 2. And then what is the resistance given? So we have here the resistance on each track based on the problem is 0.01 Newton. So that will be 0.01 Newton. Okay, that will be the resistance. And then we will have here at the same time our T sub 2. We're going to have your T sub 2. Next, let's proceed. So let's have your another track here. I hope this will be enough. Let's have your other track. 2 is just right first, so it will be 3. And then part 1, let's make it red. Okay, 4. I suppose these are the small tracks, so it's not visible. Let's try to adjust it. Let's try to move over here. Okay, so basically all the informations here on the 4 tracks will be the same. Okay, it will be the same because based on the problem, each of them, when empty, have a mass of 0.2 kilograms. So in addition to that, based on the problem, they will have an additional mass of 0.1 kilograms. So we can just copy this based on the first given. So of course, this will be your this is your T sub 1, T sub 2, T sub 2. So this will be the next will be your T sub 3. Here, this will be T sub 3, of course. And then the weight is the same, so that will be 3 Newton. So going upward, this your R going up. And then here, the same thing, we're going to have 0.01 Newton. 0.01 Newton. And at the same time, we're going to have here your T sub 3. This will be your T sub 3. Next, here, going forward, we're going to have your T sub 3 as well. Wait, let's check the coupling first. This is T sub 1. So here, oh, it must be T sub 1. There's an error. So it must be T sub 1, T sub 1, T sub 1, T sub 2. So this must be T sub 2 also here. This must be T sub 2. So you need to be very careful with the diagram. T sub 1, T sub 1, T sub 2, T sub 2. So this will be T sub 3. So here, on the other side, this will also be T sub 3. So it's the same. T sub 3, T sub 3. And then, the given resistance here will be the same as well. So we're going to have 0.01. So it will be 0.01 Newton. So the same thing, same resistance. And of course, this will be your T sub 3. So T sub 1, T sub 1. So this will be your T sub 2, T sub 2, T sub 3, T sub 3. And the last, this will be your T sub 4 here. This will be the T sub 4. So we will just write here T sub 4 because the space is not enough. So we already know that there are 4 tension so in each coupling. So basically, the weight of the 4 coupling will be the same. I mean, on each track will be the same. So here, this will be also 0.01 Newton. And the weight is also 3 Newton because they will be the same based on the problem. This will also be 3 Newton. So just take note that all of the information on each track will be the same for all. It will be the same for all. I'm just making the illustration or the diagram small because the space is not enough. Okay, now let's move on. So the next thing that we're going to do is that we're going to the resultant horizontal forces on the systems are the driving force and the resistances. So we will be solving for the acceleration. Okay, we're going to treat it as a whole system. So we can compute for the acceleration. Because remember, the acceleration on each tracks here and the engine will be the same. You're going to have the same acceleration. Okay, so let's try to use Newton's second law for the system. So remember that the Newton's second law, it doesn't change, it is still the same. F is equal to ma, or the force is equal to the mass times the acceleration. Now, so if we're going to compute what are the forces based on the given. So the forces on the given will be, so we have the driving force, which is 3 Newton. Next, minus, so we're going to have the resistance of the engine, that will be 0.6, and then plus we're going to have 0.01. Remember the resistance on each track, the 4 tracks will be 0.01, so we can just have 0.01 times 4 directly. It can be like that. Or if you want to show it 0.01, 0.01, 0.01, 0.01 4 times, that would be the same. You're going to arrive with the same answer. So let's just try to control the space. It will be like this. Now, so that would be equal to the mass of your engine based on the given is 0.8. So that will be 0.8. And then, so we can have plus, so there are 4 tracks and each track have a mass of 0.3 based on the problem, right? So we can just have it directly 0.3 times 4. Or you can have 4 times 0.1 plus 4 times 0.2. It will be the same. Okay, it will be the same. So that would be equal to, so times the acceleration. So this is your mass. This will be the mass. Okay. So if we're going to compute this, we're going to arrive with, basically this will be 3. So it will be 3 minus 0.1 is equal to A. You can pause the video so you can check. So you'll be able to check the result if it's really accurate. So I'm going to check again. Times 4. Okay, so this will be correct. So that will be 3 minus point 1 is equal to 2a. So therefore, our a here, where a will be equal to 1.45 meter per second squared. So the acceleration will be 1.45 meter per second squared. So you can pause the video so you can compute and verify the answer. Okay, so the next thing that we're going to do, since we already have the acceleration, we're going to find the tension in each coupling. Okay, now when we're going to find the tension in each coupling, what we're going to do is, remember, we just need to take note that the acceleration is the same for the engine and for each truck. So we're going still to use the Newton's second law for the engine and each truck separately. Now let's start. So we're going to have 4 tensions here to be able to answer this problem. So let's start with the first one. So for the first equation, so take note that still we are using F is equal to MA. Okay, F is equal to MA. Now let's start with the first one. Let's start with the engine. This one, this part here. So that will be equal to 3 minus, the resistance is 0.06 minus the T sub 1, that will be equal to 0.8 A, because the mass is 0.8 times the acceleration. So we already know the value of the acceleration. It's 1.45. So therefore, when we will be solving for the T sub 1, this will give us T sub 1 is equal to 3 minus 0.06 minus 0.8 times the 1.45. Okay, that is the given. So therefore, we can say, you can just pause the video, guys. You can pause the video to compute. So here, our T sub 1 will be equal to, this will be equal to 1.78 Newton to decimal place. That will be 1.78 Newton. Again, you can pause the video so you can compute. Next, let's move on to the second one. That is the first tension. Next, second one. So for the second one, this part in here, okay, that part, so that will be equal to T sub 1, that will be equal to T sub 1, and then minus, so we have the resistance 0.01. Next, minus, we have this T sub 2, and then that will be equal to 0.3 times the acceleration. So the same thing. Okay, so therefore we can say that since we know already, we got the value of your T sub 1, which is 1.78 Newton, we will now just solve for the T sub 2. So this will give us, statement will be T sub 2 will be equal to, the T sub 1 is, we already know that the T sub 1 is 1.78 Newton. So that will be 1.78 minus 0.01 minus, that will be 0.3 times the 1.45. So this will give us the value of, you can pause the video again. So this will give us the value of our T sub 2 here will be equal to approximately 1.34 Newton if we're going to express it into decimal place, approximately like this. That will be your T sub 2. Next, let's proceed to the third one. We have your T sub 3. Okay, let's proceed to your T sub 3, or this is the first, this is the second, this will be the third. Okay, sorry, this will be the third. Okay, T sub 3. Again, this is first, second, third. Okay, now for the third one. For the third one, we're going to have T sub 2. That will be equal to T sub 2 minus, so the same, we're going to have 0.01. Next, minus the, wait, let's erase this one, minus the T sub 3, and then is equal to the same thing, 0.3a. So therefore, we're going to solve for T sub 3. If we solve for T sub 3, this will yield to, so T sub 2 is already given here. That will be 1.34 minus 0.01, and then minus 0.3 times 1.45. That is the acceleration, remember? So this will give us the value of your T sub 3. So that T sub 3 here, we're going to express into decimal place. This will be approximately, you can pause the video guys if you want to solve for the value. That will be approximately 0.8 0.89 Newton. That will be 0.89 Newton. And the last, for your T sub 4, of course, for the T sub 4, that will be equal to, so T sub 4 shall be the last, minus, write it clearly, sub 4 minus 0.01 is equal to 0.3 times the acceleration. So since this is already the last, we can just compute it directly. Okay, we can just compute it directly. So we will have here, you can pause the video. So our T sub 4, we're going to substitute the values in here. So that will be equal to, T sub 4 will be approximately 0.45. We're going to express into dP. So 0.45 Newton. T sub 4. Okay, 0.45 Newton. So we were able to answer. So the tension in each coupling, for the first coupling, we're going to have 1.78 Newton. For the second, we're going to have 1.34 Newton. For the third, we're going to have 0.89 Newton. And for the last, we're going to have 0.45 Newton.